The thing is, it's a wide end. You have to be very close. Nou, dat weet je maar nooit. Als we hier zo staan te praten, kan Bert het vast horen. Ja. Dan is het geen geheimtaal meer, als Bert Wijnen het wordt. Dat is een goede ding. Hey guys, this is Alex. Hey. No, there's one more. No, she's yeah, if that's the problem, then we need to figure out a name. Yeah.
Okay. Maybe that will come up here. Oh, because of the talking down there. I can run the slides for them up here, and that should be up here. Yeah. I'm displaying the wrong thing. Oh no.
Yeah, so that is not.
Lars here. It's a very awesome one.
So this is being streamed. So if you tune into the stream, the live stream, we can basically see your slides on the screen. That's
I know, but I'm not ready. I'm not ready. I didn't think I had to figure out this system. Here, let's do blue sheets. Hi everybody, new IRTF here. Don't know how to run it. Presentations, I have a short amount of time. So may I direct you to the agenda? You can put your slides on your screen. All right. Oh, I love this. Okay, hello. I need to actually project, but I also need to not have anything else up here running, which is a problem. So let me kill off the things. For some reason, I thought there would be a machine. I would not be using my old machine. This is my mistake. I don't know. Actually, I think that's something that. This is what I want. Yep. Okay. So our agenda today is a brief overview of the area by me, and then our first two awardees of the Applied Networking Research Prize. And those are going to be great talks. And you've all, I think, seen a slide that Lars has put up many times before, where he shows you that we're under the same IPR policy as the IETF. So note that. There's a little bit more detail to it if you look at the slides on the page. I have a slide coming up that will tell you where these slides are, but you can find them in the agenda of the data tracker. I've just updated a new copy, so if you downloaded a copy a while ago, you think that the deadline for the ANRW workshop is June 3rd. It's not, it's April 3rd. So don't believe your slides if it says that you have 2 months ahead. Okay, here we go. So there's the, I think I'm not want to do a slideshow. No, stop. Okay. Okay, so the IETF IPR policy read it at your leisure, but bear in mind that we are under IPR according to RFC 3979 here, in terms of disclosures, etc. If there's a remote participation, we do have a lot of people on Meet Echo. I will try to manage if people want to do the queue. We have, hopefully we have somebody who would be willing to watch Jabber and let us know if somebody asks a question on Jabber. Can I get a hand for that? Thank you, Matt. Okay, and as you probably know, we have mailing lists, IRTF Announce and IRTF Discuss. Join those. The prize talks are by Yossi Gilad and Alastair King coming up. So Lars handed off the chair to me this morning, and I just wanted to say about Lars that he has been an astoundingly great IRTF chair. It's really humbling to follow him. He's been devoted for 6 years to the excellence, the openness and reach and breadth of the IRTF, and he's been a very innovative chair, including starting the Applied Networking Research Prize and the workshop. So let's get a round of applause for Lars. There's a workshop. This will be the second of them, and it will be held at the same venue as IETF in Prague on the Saturday of IETF week. We really want great submissions. This is up to you. Submit papers for this. And the deadline and the location for submitting papers is there April 3rd. I will eventually get used to the mic. IRTF meetings, we have about 10 groups. 7 of them are meeting this week. I've listed them. There's groups that are not meeting, but some of them are having interim meetings, Crypto Forum and Global, Gaia, Global Access to the Internet for All. And important news is that this IETF's technical plenary is on the theme of human rights protocol considerations. And one of the chairs, Niels Tenover, and the first chair of the IRTF, Dave Clark, are speaking to us about this. And it should be a very interesting and lively discussion, so come to the plenary. It's been a little bit quiet in the stream, just one publication, but a number of others are queued up. And we concluded a couple research groups after the last meeting, SDNRG and the provisional or proposed network machine learning group. As always, contact me about your interest in forming new groups or any comments you have on the existing state of the area. And with that, I'm going to turn the mic over and the floor over to Yossi first for the talk about path and validation extension to the RPKI. No, you don't.
Hello. So I'll present Jumpstarting BGP Security. And this is a joint work with Avichai Cohen, Amir Herzberg, and Michael Shapira. So really, this talk is all about inter-domain routing, and today's de facto protocol for doing that is BGP. And so first, let me start off by motivating a bit about the problems in BGP. So BGP carries no authentication over the data. And so let's consider the following case that shows how BGP works. So we have Boston University at AS111, and BU has a prefix. Okay, so yeah. So BU has a prefix 168.122/16, and it advertises that prefix to its neighbor ASX. And now ASX learns a route to reach the IP addresses within that prefix. So it would send its data packets down to BU. Now, not only that, ASX also relays that advertisement onwards to its own neighbor. So, so it appends its identifier to the route, and now its neighbor learns another route. Its neighbor learns a route to reach the IP address within that prefix. Now, since BGP carries no authentication, the attacker can actually provide the same announcement for the same IP prefix, and now the victim has two routes to choose from. So it can either go to route its traffic through ASX and then reaching BU, or it can route its traffic to the attacker, both claiming to reach for the same prefix. So what would the victim do in this case? Well, it would choose to go with the shorter route. So the attacker would actually intercept traffic coming from the victim. So in order to mitigate these problems called prefix hijacks, there's a new mechanism that was standardized called the Resource Public Key Infrastructure, or the RPKI. And the RPKI really maps IP prefixes to the organizations that own them. It provides, it really facilitates two things. So it provides origin authentication in order to prevent hijacks, and it also lays the cryptographic foundation behind more sophisticated mechanisms like BGPSEC that prevent more advanced attacks. So I'll talk about both of these in this talk. Let me start off by talking a bit about how the RPKI is deployed and performs origin authentication. So usually RPKI, so the way RPKI is usually deployed is the administrator deploys this sort of general purpose local cache machine in its AS, and that machine syncs with the globally available repositories. And these repositories hold the route origin authorization records, or ROAs, which provide this sort of authenticated mapping between an IP prefix and the AS number that's allowed to originate routes to that prefix. So the local cache retrieves these ROAs, and then it verifies the signatures over them. And if the signatures are valid, well, then it creates a sort of a whitelist filtering rule. So, so in this case, the IP prefix 168.122/16 should only be announced, or should only originate from AS111. And then it goes on and deploys these rules onto the routers. So in general, that's how the RPKI is being deployed. And it's slowly gaining traction. So at the moment, over 6% of the IP prefixes that are announced through BGP are actually protected by this, are actually listed in these databases. Okay, so let me show you how this allows to prevent the prefix hijack. So consider the earlier scenario. We have the victim, and the victim learns two routes to reach an IP prefix. Well, now, given that the victim observes these databases, the RPKI database, they can find that actually AS666 is not authorized to originate a route for that IP prefix. And so the route from the attacker is invalid, and so it is discarded, and traffic would flow down the correct path. But the RPKI does not prevent all attacks. So specifically, if the attacker is sophisticated, well, they don't have to claim to originate the IP prefix. They can sort of claim to be directly connected or have this false link to the true origin. So they can use a false origin in their announcement, and now the victim receives again two routes. And in this case, the RPKI does not provide any data that allows to identify that the attacker's route is false. So really, it looks like so really the victim can tell the difference, and it would choose to route its traffic to the attacker because the route in that case is shorter. So how will we protect inter-domain routing security? Well, the current paradigm has two steps. So step one is to deploy the RPKI and so prevent hijacking. And then the second step is to deploy BGPSEC. And BGPSEC protects against these false paths that attackers might try to claim in their advertisements. The way it works is, well, consider the router at AS111. Well, BGPSEC adds this new attribute called the secure path, where now the origin, AS111, would sign the announcement that it would send to its neighbor, ASX. So that would allow ASX to, and so now ASX would need to do two checks. So check number one is that AS111 is the actual legitimate origin for that prefix, and the second check is that the origin actually approved the next hop. If that is so, well, then ASX would actually sign, would add the next hop, so its own neighbor to the route, and sign the new announcement. So now the announcement has actually two signatures on it, and when AS1 receives it, when ASY receives it, it would now check that the origin is correct, and then that the link between AS111 and ASX exists, and also that the link between ASX and ASY exists. So basically, it would the number of signatures verification would be the number of hops. So BGPSEC allows to identify these false links, but it also presents a significant deployment challenge. It requires to perform real-time signature validation, real-time signing and signature validation. So routers need to do a lot more effort, and they probably need to get upgraded. And that seems to suggest that we're going to have sort of a long period where BGPSEC is being rolled out, but BGP still exists. And the second thing is that BGPSEC actually changes the BGP message format. And so that might suggest that during that long period, we're going to have some compatibility issues. And so what are the benefits of BGPSEC under partial adoption? Well, so consider the same topology. Now all the ASs in blue adopt BGPSEC, so almost all the good guys adopt, except for ASX. And that means that AS111 actually can't advertise its prefix in BGP because ASX does not know how to handle secure paths. And so, in a sense, ASX actually breaks the BGPSEC path. And it would force AS111 to advertise its prefix through legacy BGP. So now the attacker can actually do the same attack as it did before. It only needs to circumvent the RPKI because the victim receives a legacy BGP message, and therefore, again, traffic would flow to the attacker. So really, it was shown that under partial adoption, BGPSEC provides only meager benefits. So in this talk, our goals are, well, there are really two goals. So on the security side, we would like to protect against these like forged origin attacks in BGP advertisements. And we would like to provide some significant security benefits even under partial adoption of our protocol. So that is in contrast to BGPSEC. While on the deployment side, we'd like to do some minimal computations and have them be done only offline and off the router. So, so we won't need to change the routers, and also we don't want to change the BGP messages so that we won't run into these compatibility issues. So really this is very similar to the way RPKI is being deployed today. So we're proposing to do pattern validation, and the way pattern validation works is very similar to the RPKI. You have a database, and that database allows an AES to also list its neighbors. So in our case, AS111 would also register that it is linked with ASX. And if that database covers all the neighbors, then the victim can now identify that there is no link between AS666 and AS111, And so it would know to discard the attacker's route and send the traffic in the correct path. Let me just briefly summarize the result that I'm going to show you later. So how much security would that small sort of additional mechanism buy us? Well, so this diagram shows shows on the y-axis the attacker's success rate, and on the x-axis it compares between different protocols. So the blue bar indicates just vanilla BGP. So what happens when we have no authentication? Well, the attacker can do hijacks and get about 50% of the traffic to the hijacked network. If we add RPKI on top of that and we have origin authentication, now the attacker gets about 30% of the traffic. Doing path end, you get further down to just below 14%, while the purple bar shows what happens in the best scenario, where in the best partial adoption scenario for BGPSec. So that means that everyone adopts BGPSec, so everyone supports it, but still legacy BGP messages are allowed. So the attacker can still advertise in legacy BGP, although everyone actually speaks BGPSec. And you can see that in that case, BGPSec actually would provide around 10%. So the difference between patent validation and BGPSec under partial adoption really, even in the best case, cannot be that much. So conceptually, if RPKI allows an ASD to claim ownership for a prefix, patent validation sort of extends that to also authenticate the link between V and D. And it would allow any AES, say in this case ASA, to check whether the link between D and V actually exists. So just to provide sort of the intuition as to why this would buy us some significant benefits, well, the reason is that the average path length between AESs on the internet is actually quite short. So it's about 4 AES hops long on average. And that seems to suggest that if the attacker is forced to sort of use and to sort of add another hop to its route, then its route is going to be much less attractive. So how does patent validation deploy? Well, very similarly to the RPKI, you have a database, and the local cache retrieves the ROA, but it also retrieves this edge authenticator record from the patent database, and it checks the signature, the signatures for both of them. Nothing is, no crypto is done on the routers. Now, if that goes through, well, now the local cache deploys a filtering rule. Not only that 168.122/16 needs to originate from AS111, but it also ensures that if AS111 is on the route, it should be followed only by ASX. And the cool thing about this sort of deployment strategy is that actually routers today support filtering rules by of BGP advertisements by the AESs on the route. So you can use the existing ACL interface to configure a filtering rule that would filter that would filter out if the hop following AS111 is not X in this case. And in addition to that, since you only add this one rule per AS number, the more AESs who adopt, actually the longer the prefixes that are authentic, the longer the suffixes that are authenticated. So in this case, if ASX joins the system and registers its neighbors, well, now the attacker needs to spoof a 2-hop route to the actual origin. So finally, we evaluate the security benefits that such a mechanism would buy us on today's internet, and in order to do that, we use a simulation framework. So we have the internet level AES graph from CADA, and in each iteration of our simulation, we pick an attacker and a victim pair. And we assume that the victim adopts both the RPKI, so it registers its prefix in the database, and also registers in the pattern database. So, so in that case, ASA lists that it is linked with ASD. And then we pick a set of ASs who are doing filtering. And for different attack strategies, we measure the percent of ASs who are full to take the attacker's route. So basically, that's the attacker's success rate. So let me show you some results. So in this graph, you can see the attacker's success rate on the y-axis, and on the x-axis, there is the amount of top ISPs, so the largest ISPs, who are performing the path-end validation filtering rules. And you can see that, so there are two lines here. The blue line shows what happens when the attacker does the next AS attack. That is, when the attacker claims to be directly linked with the legitimate origin of the prefix, and that is precisely the attack that pattern validation was meant to mitigate. So you can see that the more adopters that you get, the attacker success rate goes down. And even with 20 adopters, actually, this attack, the attacker should not perform this attack because it should claim to be connected to a neighbor of the legitimate prefix owner and circumvent pattern validation. That would give him about 14% success rate, regardless of the amount of filtering nodes. So that is the point where the attacker should switch. And just to give you context, so the dotted red line here shows what you would get with the RPKI, while the green line shows the best that you could hope for with BGPSec under partial adoption. So again, that is what happens when everyone adopts BGPSec, but BGP messages are still allowed to be advertised. So it wasn't deprecated yet. And for comparison, the purple line here shows what would happen with BGPSec being rolled out with this set of ASs who are adopting. So you can see that BGPSec would provide almost no benefit. Another interesting result we found was that actually local deployment can provide protection for local traffic. So this is particularly important since many clients are fetching content from nearby. And now on the x-axis, this graph plots deployment just on the North American ISPs. And for the attacker and victim pairs, we picked just ASs within North America. And as you can see, also, quite quickly, so even with the top, with only the top 10 ISPs adopting, the attacker's success rate doing the next AS attack goes down really quickly. And so we should switch to doing the two-hop attack, which buys almost the same success rate as the best you could hope for with BGPSec. We've also seen similar trends in Europe. So this is not just for North America. And finally, you might ask, well, why shouldn't I authenticate more than the last hop? Why shouldn't I authenticate the neighbors of my neighbors and list them in this database? Well, so doing so is much harder because while the operator knows the ASs that are directly linked to it, it might be harder to know the ASs that these neighbors are directed to. And furthermore, you can see here so here on the graph, I would argue that it buys you not that much additional benefits. So on the x-axis, you can see how many hops from the actual origin does the attacker claim. So for different amounts of hops, of false hops in the advertisement, and on the y-axis, the attacker success rate. So if there is no authentication with just vanilla BGP, the attacker can claim to own the prefix, so it can do hijacking, get about 50% success rate. If RPKI provides origin authentication, it goes to about 30%. Pattern validation leads you to 14%. And the two-hop validation really gives you not that much benefit further from that. We have some more results in the paper. So in particular, we found that large content providers are actually better protected by pattern validation. We also found that pattern validation could have mitigated some high-profile incidents that occurred in the past, And finally, we also prove that it is security monotone. So if an AES decides to do filtering, that means that no other AES can actually get a bad route. That's not true for all routing security mechanisms. So just to conclude my talk, so I present pattern validation, which can really significantly improve inter-domain routing security even under partial adoption, while circumventing all the deployment hurdles that BGPSec has. So really advocate sort of extending the RPKI to allow this option of an AES to register its neighbors, given that the similar actually the identical deployment strategy. And finally, if pattern validation is standardized, we recommend some efforts, financial or regulatory, in order to gather this small but critical mass of adopters who should do the filtering in order to get all the benefits. So with that, I'd like to thank you for listening and conclude my talk.
Hi. It's about 10 minutes for questions, so go for it.
Russ White, LinkedIn. We may all have the same question, Eric, and Doug may even say the same thing. So I'll just suggest that you said that if you could get providers to deploy this, I would actually suggest, well, you might want to talk to Leslie Daigle if she's over there someplace. She's leaving the room. Run, Leslie, run. We have been working as a small group to do work around some BGP security stuff. Similar to this, you might want to go back and look at the SOBGP work. You may have already looked at it, and PGPGP, which are all kind of in the same area to some degree. My only suggestion would be is that you're never, ever, ever, and Eric's going to tell you the same thing when he gets up here, going to get transit providers to deploy this. Won't happen. Your best hope is to get people like LinkedIn, Microsoft, Google, Facebook, the big eyeball providers on the edges to deploy this. And people who are directly connected to real customers, I don't mean real customers, but I mean like Time Warner Cable, people like that who provide residential service and business service. The reason is contractually, a lot of your transit providers cannot legally tell you who they're connected to. Fact of life. However, as LinkedIn, I can tell you who I'm upstreamed to. So if you're ever going to have a hope of getting this type of thing off the ground, it's probably going to have to come from the edge in and have people like LinkedIn advertise an RPKI or some other way who my upstreams are. You're never going to get level 3 to admit to the public that I'm using them as my upstream.
Right. So let me just respond. So most of the internet are stubs, so they should be able to join such a system.
No,
but well, they only have if you only have one provider, then you might be. We also have some ideas on how to avoid these issues.
Yeah,
I'd be happy to talk later.
Yeah, I'm just telling you practically.
Yeah,
you're never going to get transits to do this. That's all.
Yeah. Okay.
Doug Montgomery, NIST. So when you're comparing these attack results to full BGPSec, what policies did you assume were being implemented around BGPSec?
So we basically assumed the standard type. So we basically assumed that if you get a secure path and an insecure path, right? Is that what you're asking, right? What would you pick, right?
Yeah. Well.
Yeah.
What?
So
you had to assume some routing policy.
Right. So we assume that you break ties according to the secure path. So if you get an insecure path and a secure path, so a path that's advertised through BGP and a path that's advertised through BGPSec, you would prefer the secure one.
So in your graph where it says BGPSec but permitting legacy, you assume that there is no fully signed BGPSec path for that prefix.
No. So imagine that the victim actually gets a BGPSec fully signed path, right? But it also gets a BGP path, but the BGP path, say, is shorter, or is less expensive. So
for sure, your policy isn't to always prefer the.
No, not always. Break ties. break ties with the secure path.
So I think that's a key point about that result, is that it assumes what the policy is around.
Right. So yeah. So that is the policy that we assume.
Hi, Eric Osborne, Level 3.
Hi.
I admit to not having read the paper. So I'm not going to ask you a question. I'm going to ask if the paper covers it, because I think I missed it in the presentation. It's easy to fake out RPI, because if you're attacking AS as 666, it just adds an AS path that says 111 behind it, right? But if I am 666 and I say X 111, haven't I defeated this whole thing? Does the paper explain it? And I'll go away. I'm not here to ask dumb questions.
Right. So yes, and I've tried to convey that in my presentation. So actually, if you do that, then your advertisement would be less appealing, because you had to sort of, it would be less attractive to the victim, because now you've had to sort of add this additional hop to the route, right?
So your whole scheme relies on short AS path to beat this.
Right.
So if there's any AS path padding in the original 111, you...
no, so that means by padding, you mean that you would repeat the same AS number?
Yes.
Yeah, that's still fine. So if the number of different ASs on the route stays the same.
Okay. I think I understand, but I'll go read the paper.
Okay.
Okay, Oliver Borcherdnis. I have two questions. The first one is, if I understand you right, then the database, what I have to maintain is fairly large, because I don't only have one originator, I have many originators, and I have for every originator to store or to parse their particular peer. Therefore, the policy processing becomes, I would imagine, bigger. So the interesting thing here would be, what is the overhead in processing just for the additional policies what you have to now inject into the router? That's number one. So, and number two is, your graph shows basically that you only are better in 1, 2, and 3 hops pretty much. So the average path length, as far as I remember, is somewhere 3.7 or something like that. So the AS that basically, I think it was AS666, already has a punishment of one hop. So therefore, it doesn't win over 3 hops, it only wins over 2 hops, what basically makes the path relatively short. So another question is, what is the gain, what you make, considering all these? Together with, normally when I already implement BGPSEC, so I can validate the secure path and have a secured one and I have an unsecured one, I always would go with the secured one.
Well, okay, so I guess for the first question, I would argue that it is less than what you would keep to maintain the BGP routes, right? So the database size, if you're worried about the database size,
you have basically, right? The database
so,
size you have for every origin, you have
you have the outgoing policy. Edges, right?
So the way how I understood it is that you have a policy processing for every incoming origin announcement.
So for every
your policy has to be, and I have to say I'm not really deep into the policy processing, but just from my imagination, I could think that I would have an awful lot of policies I have to process to even get to the point to say, hey, yes, I can take that.
Well, so think about how many policies similarly you would have for the RPKI, right? You would have for each prefix, you would have an AS number, right? So we're saying for each AS number, have a regular expression that describes its neighbors, right?
Yeah, but you don't. So, you say that you still keep RPKI. So you put it on top of RPKI. So now I have already the policies for RPKI, and
right.
Now I have additional policies.
Right, but the number of so the number of AS numbers on the internet is actually smaller than the number of prefixes. I'm not saying it won't have an overhead, but the overhead that you're paying for the RPKI, like the amount of data that the amount of state that you need to keep for doing the RPKI filtering, is actually about an order of magnitude more than what you need to do this mechanism. So
the
if
only,
you're
the
doing,
only thing what I say, it would be interesting to maybe make some measurement in that,
Yeah.
just to come back and say, okay, that's actually the processing overhead what we would expect.
yeah, yeah,
I know
no,
there are
I
many
agree.
other
So we
things.
didn't experiment with real hardware. Now for the second question, yeah, so the entire, I guess, gain comes from making the attacker use this additional hop, and I would argue that this actually makes a big difference in practice.
Hi, Gaurav Dabra from Cisco.
Hi.
I actually have the same question as the two questions I have. One is what Russ brought up about the deployment use case, right?
We're going to
One
cut
of-
the mic. I'm
RPKI has
afraid,
been out there
after.
for some time, and we have not seen massive deployment for it. Part of the reason is the upstream service providers do not want to deploy it. So, what have you thought about, like from a deployment point of view?
Yeah. So you're right. So we really sort of imagined the ASs at the core of the internet doing the filtering, not as much as registering themselves through the database. Well, if you're a content provider, then well, it is in your interest to you're not providing any present services, right? But it is in your interest to deliver your content correctly.
Right,
So-
but keeping it centralized like a database on the service provider rather than actually distributing the information from
Oh.
edge providers.
Oh,
might
I
be
see.
better.
You're asking, can we distribute these these
Yeah.
databases? Yeah, we actually we are thinking of that.
Okay.
Yeah.
The second question I had was similar to the gentleman in front of me was the performance impact. I actually implemented it on Cisco hardware. There is a hit, of course, when you have to do the comparison for every prefix, for millions of prefixes. I think it'll be good to see what's the difference you will see with your idea versus what we already have.
So yeah, I would love to chat with you offline about that. We actually we tested it in software, but not in hardware. So it should be interesting to check.
Okay.
Yeah.
Alexander Azimov from Curator Labs. Could you please correct me? If the only improvement compared to RPKI is that if I want to hijack your network, I need to add one more hop.
Mm-hmm.
So
Yeah.
this is the only difference.
Yeah.
And what is the reason?
So what is the reason? Okay.
Yeah. So okay, I will hijack the network. My upstreams will choose my my prefix.
Yeah.
Whatever length of these in-IS path, because they will because BGP, unfortunately, it's not a distance vector protocol. It's more about money or priorities.
Yeah.
And so when I will hijack your network, all my providers, direct or indirect, will choose my announce. And still, if I, for example, level 3 will choose my prefix, I will have a lot of your traffic, and so I will reach my goal.
Right. So this actually comes to play in our simulation. So we did take into account the inferred business relations between these ASs. So if one AS receives an advertisement from its customer, we did assume that it's going to take that over the other, basically.
My point is that even if I will affect 10% of internet, it could be 10% of a very important part of internet.
Oh, I see.
So
yeah,
different autonomous systems have different reachability, different customer base, and so I would rather think twice before making additional security mechanisms.
Well, okay, so you're right in the sense that 10% of the internet might consist of very important users, right? Yeah, so we didn't weigh the ASs in our metric. We basically counted the number of ASs. That would be an interesting thing to add to the simulation framework in order to sort of rank the attacker. Yeah, I don't know. I have no intuition about would this 10% be the best ones or not. I'd be happy to check.
For example, L3 will be an important part. Okay, thank you.
Okay, thank you very much. And obviously, I know. Allison, talk to the mic. I understand you're also presenting another session in the IETF, so people can come and hear this again. The routing area, is that right? Yep. Okay. All right. So next is Alistair King, and he's going to talk about BGPSTREAM. Thank you very much. We're still on time, actually, so that's good. So a couple of people didn't give their names at the mic. When you come up, make sure to give your names. I'm actually taking notes in the Etherpad.
Hey, good afternoon. You guys can hear me all right? Okay. So I'm Alistair King from CADA. This is the Center for Applied Internet Data Analysis at UC San Diego. And I have the pleasure of talking to you this afternoon about BGPSTREAM. And this is a software framework that we've developed for the historical analysis and real-time monitoring of BGP measurement data. And this is some work that we presented last year at the Internet Measurement Conference in Santa Monica. So BGPSTREAM, as I said, a set of open source libraries, APIs, and tools for historical and real-time BGP data analysis. Open source, it is open source now. It's available. It's been released for about 1.5 years now. We've had several publications that have already used it from other authors. I think actually Yossi used it for some of his research. And so, I mean, a big part of this presentation is going to be really an encouragement to this community to go out and look at it, use it for your research, use it for your maybe for your operations, and also we were really wanting feedback from this community about things you would like to see changed and other things like that. So BGPSTREAM, we've really tried hard in this case to come up with a simple way to do potentially really complex analysis of BGP measurement data. We've designed it for use by both researchers and operators, so we'd really like some feedback from more of the operator, real boots on the ground side of things here. We're certainly happy as researchers, but on the other side of things, that's where we're looking for some real feedback. As well, I'll also show you how when you're using BGPSTREAM for doing research, for doing analysis, it really facilitates experimental reproducibility and repeatability. And then, as I've said, it'll do real-time monitoring just as easily as it'll do historical analysis of BGP data. So first, you may be wondering, why create this software? What is it doing? What's the need that it's filling? So as researchers, and especially researchers who are looking at BGP data, we make use of a ton of this existing BGP measurement data. So there's these two major collection projects in this space. You may have heard of them, Route Views, the University of Oregon, and then the RIPE-RIS collection effort. And so between these two, they've been collecting data, each of them actually for over 15 years now, and they have something like 20 terabytes, maybe even more, of collected MRT data for the last 1.5 decades. And so we've been using this data a lot, but when we started at CADA developing these large-scale platforms for doing real-time data analysis with BGP, we really found that there was a real lack of good tooling for processing and analyzing BGP data. And so, when we would go and try and do this, the state of the art in this case would be something like go to the Route Views website, browse around, find the file that I want, download it to my server, and then use BGP dump, convert that to ASCII, pipe it through some kind of parsing script that I just hacked together for the purpose of my analysis, and then, of course, rinse and repeat for all of the files that I was interested in. And so this really is just sort of a small snapshot of this type of thing that we're trying to make easier with BGPSTREAM, but it's also capable of doing a whole lot more than that I'll show you throughout this presentation. Okay, so how does BGPStream work? If we sort of go up to a really, really high level, BGPStream, the framework is a distributed framework. It's comprised of these two main components. The first is the metadata broker. So this is a web application that we are running an instance of at CADA. And this can be easily replicated elsewhere, and I'll talk about that a little bit later on. And then the other component is a set of user libraries. So this is software that's run by users on their machines. And so what happens, the metadata broker, this web application has this background process that's continuously crawling and indexing the data that's available on these public data archives. So the instance that we're running at CADA is continuously crawling the route views and RPKI archives. And it's able to serve queries about which data is available there. So I just want to stress here, this metadata broker service that we're running, this isn't storing actual BGP data, it's storing the metadata about what's available, and it's not serving BGP data to users. The way that the actual data gets served is instead the user library, so this is software running on users' machines, first sends a query to the metadata broker, and then based on the response to that query, these libraries will actually go out directly to the provider's archives and pull back the data that needs to be processed. And it's going to do this over HTTP, over the standard public interface to these archives. And as the data is being retrieved, it's processed on the fly by this stack of components that are running, again, on your machine, doing analysis that you want. So another way of looking at this framework is sort of maybe in a more rigorous fashion. If we stack it up, at the bottom in this sort of layer 1 here, we have the data providers, route views, the RPKI, and then the metadata providers, of which our metadata broker web service is like an instance of this metadata provider. And then the center here, we have libbgpstream. This is a C library that is really the core of the BGPStream framework. And it's responsible for going to the metadata providers, for going to the data providers, and retrieving the data, and then demultiplexing that into a single stream for this top layer, this level 3, which are your applications. These are users' applications written in C using a C API, Python, and then we have some other tools that make it easier to do sort of large-scale, complex analysis of BGP data in real time. So I want to point out the blue boxes in this diagram. This is a diagram we present in the paper. The blue boxes are software that we've developed as part of the BGPStream framework. So the orange things are these third-party components that we're using. And then anything in a blue box that's also marked with a star, that's software that we've already made publicly available as open source. So in the center of the stack here, as I mentioned, we have libbgpstream. So this is the core part of our framework. And before I talk about this, I wanted to say, so in BGPStream currently, we are only supporting the MRT data format. This is sort of the de facto standard, at least currently, for capturing and storing BGP measurement data. There are absolutely efforts to replace MRT with other things. So we have BMP, and we're currently working, we have a collaboration with Cisco and their OpenBMP guys to add BMP support to BGPStream. And that's going to allow us to get a lot lower latency access to BGP data, as well as, I know RPKI, I can see Robert here, they're developing a new streaming interface for their BGP measurement data. So that said, for the moment, there's this wealth of MRT data available. As I said, with this 15 years of MRT data, and it's continuing to be collected. So as we speak, more and more MRT data is collected. So for the rest of this presentation, we're going to be talking about BGPStream, and the assumption is going to be we're processing MRT data. Okay, so libbgpstream, this core part of the framework, as I said, it'll go to the metadata broker service, figure out which data it needs to download, go directly out to the data provider's archives, pull that back over HTTP, and then demultiplex this data that's coming from potentially multiple sources into a single stream. And so in this way, you're able to configure BGPStream to retrieve data for example, all of the route views, all of the RPKI collectors, which ends up being something like 300 and maybe 400 BGP peers worth of data, all demultiplexed into a single stream for your application to process. And an important step in this demultiplexing is sorting. So we do this best effort sorting when we're pulling the data back from the providers to present it to the user in a time-ordered stream to simplify their analysis. And so if you're interested in the sorting, there's some more details in the paper, and I can also talk to you later about that. So as I mentioned, libBGPStreams, the C library has a C API, and we've really tried to make the C API as usable and intuitive as it can be for a C API. We expose two types of data structures. The first is a record. So a record really is just a really thin wrapper around the MRT record. And the reason we add this wrapper is so that we can add some metadata that's not found in the MRT. So for example, the name of the collector that this record came from, and then the collection project, for example. And then so because these MRT records that we're wrapping here, these can contain information, one record can contain information for multiple prefixes or multiple peers. So in the example of a rib dump, so this is a table snapshot that comes from a collector, the routing table snapshot. A rib dump record inside of MRT can actually contain information as seen by multiple peers. So it's all of the routes, for example, to one prefix as seen by the peers of the collector. And so to simplify processing here, what we do is we decompose this information in the record into what we call alums. And so this is just information about a single prefix as seen by a single peer. So here is some code. This will instantiate an instance of BGPStream using the C API. The highlighted part here is perhaps the most interesting, if you can see it on these screens. First of all, we add a filter that says I only want data from the RRC06 collector, so a write risk collector, as well as I also want data from the route views jinx collector. And then next, I add a filter that says only give me the updates information. So, you know, implicitly it's saying don't tell me about the rib dumps, about these table dumps, only give me the update stream from these two collectors. And then, of course, we specify a time range that we're interested in processing data for. So once we've done this instantiation and configuration, we then have this set of nested while loops where we first iterate through the records from the stream, and then for every record, we iterate through the alums of that record. And so this kind of structure, the overall structure of this API is going to be reminiscent of like a libpcap, a libtrace API for those of you who have done passive traffic analysis. And that's definitely intentionally wanted to model this on something that was familiar in this space. So as well as C, of course, we have Python, make life a little bit easier. In the paper, we use the Python bindings to implement sort of a commonly, or at least in the past, it's been a commonly studied facet of BGP, and this is AS path inflation. And so, you know, the point here on this slide and with this implementation wasn't to say, hey, we studied AS path inflation, it's interesting. No, instead it was to say, this is something that's been tackled in research, and in the past it required you to do a lot of work as a researcher in order to get access to the data, in order to process the data. But we were able to do it with BGPStream, with the Python bindings here, and actually we're able to do it in something like 30 lines of code. And then what's actually even cooler on top of this is that not only do I have my analysis logic in my code, I've also embedded the data specification. So as a usual disorganized researcher, I come back to this a year later, and I don't need to remember what the data was that I processed to get these results. It's actually embedded in that same script. So not only can I remember, but now I can hand the script off to another researcher who can take that, use that to reproduce and repeat my experiment. And then, you know, finally, of course, the Python bindings are just bindings to the C library. So you get that power, the performance of the C library, but available through a much more intuitive Python interface. So another thing that we did as a case study for using BGPStream, we took those Python bindings, and in this case, what we did is we were looking at using BGPStream in a real-time monitoring context. And so what we did is we looked at community-based black holing. And so this is where the victim of a denial of service attack makes an announcement for a prefix that's under attack, and it adds a special community attribute to that announcement, which requests that its neighbor or neighbors drop traffic destined to that prefix. And then using PyBGPStream, these Python bindings, we monitor BGP in real time, near real time. And as soon as we see one of these announcements, we then trigger trace routes using RIPE Atlas and then watch for withdrawals. So and similarly, when we see a withdrawal for the prefix, we trigger more trace routes. So we end up with this data set of trace routes that are taken during a black holing event, and then trace routes that are taken after the black holing has finished. And then we're able to compare the results we see between them. And so the results in and of themselves are interesting. If you're interested in those, take a look at the paper. But the point here again is what we were able to do with using these Python bindings and the real-time monitoring capabilities of BGPStream, we actually found that we're able to, for 90 to 95% of these black holing events, we're able to probe the black hole prefix while the black holing was still in effect. And so in this way, we're able to combine this passive control plane data with active data plane measurements and look at these timely, these transient routing policies in effect. So, I've talked about with our C API, we have this Python API, and then we also make available this command line tool that we call BGP Corsaro. And this is a plugin-based tool, and its job here in the BGPSTREAM framework is to allow users to do continuous real-time monitoring of BGP, but in more of a, let's say, a production or operational capacity. And so what it does is it continuously monitors this BGP data that's coming in from these public data sources. And then it runs some analysis logic and then outputs statistics or some outputs some aggregate statistics in these regular time bins. And so this is probably better demonstrated through an example. We make available with BGP Corsaro a sample plugin. This we call Prefix Monitor. And so this plugin, you give it a set of IP ranges. So this may be your network, something that you're interested in monitoring. It then watches the BGP data as it comes in, and as it's tracking only two statistics. One is the number of prefixes that are announced from that address space, and two, the number of origin ASs that are announcing those prefixes. So we took this plugin, took BGP Corsaro, and we used this to look at a hijacking attack that was first reported by Dyn Research in January 2015. So this is the Italian research network, GAR. And you can see the output from the plugin here. On the left y-axis, we have the number of prefixes that are announced from GAR's address space. And then the right y-axis, and so the blue line here, we have the number of ASs that are announcing those prefixes. And so you can clearly see these 4 spikes there where the number of origin ASs goes from 1 to 2. And indeed, the spike on the 7th is exactly the event that Dyn Research was reporting on this blog post here. And we dug a little bit more into the data and found there's some Romanian AS that's also announcing GAR's address space here. So, again, the point here isn't, hey, we have a perfect hijack detection tool. It's, hey, we have a platform that if you have some kind of operational monitoring you want to do, and so real-time monitoring you want to do, this might be a good place to start from. Oops. And then, of course, we have 15 years of BGP data. This turns out to be a lot of data. We said, hey, maybe this is big data. And so we went and took the Apache Spark framework, BGPSTREAM, put them together, and then made them work happily together. And so in the paper, we present sort of some results from this analysis. And I'm going to go really quickly through a couple of those things, a couple of the results we got out of this. But again, the point here is we did the work to see how you can use BGPSTREAM in this big data environment. And we've also made available some of these scripts as templates that you can use for using BGPSTREAM in this way, looking at longitudinal analysis of BGP measurement data. So just really quickly, some results from this analysis. Of course, size of the routing table over time. But actually, what kind of surprised me, and maybe this shouldn't have been surprising, we ended up needing to use this routing table size metric to normalize a lot of our other analyses. And it turns out that as this heat map really clearly shows, so this is the size of every peer's routing table over time. And you can see the expected curve there at the top. And then there's this other mess at the bottom. And so these are what we call the partial peers. So in this publicly available data, there are many peers that are only sharing a fraction of the global routing table. And so in order to get this number, of the size of the routing table so that we can then normalize our other analyses, we have to exclude these partial peers. Otherwise, they end up skewing this calculation for the size of the routing table. Okay, so next, we took a look at the prevalence of transit ASs over time. So in this case, we are just defining a transit AS as an AS that at some point appears not at the edge of an AS path. So it's somewhere in the middle of an AS path. And on the right y-axis here, we have for both V4 and V6, the total number of ASs that we see at each point in time. And then similarly, on the left y-axis, we have the fraction of those ASs that we classify as transit. So if we first look at V4, the red lines here, you can see this sort of almost a flat linear growth in the overall number of ASs in V4, but the number of transit ASs here has actually been remarkably flat over time. Contrast that with V6, on the other hand, where there's this steady decay in the fraction of transit ASs. So it's been suggested to me that this is perhaps because the core of the internet is already close to 100% V6 ready, and maybe what we're seeing here is instead the growth of the edge in V6. I don't know. And so then finally, the last thing that you can, and maybe probably my favorite thing that you can do with BGPStream is building this complex monitoring infrastructure that monitors the entire internet in real time, 24/7. And we did this, so this was actually the reason why in the beginning we developed BGPStream. So we have these two projects at CADA, one that was detecting or detects large-scale internet outages, the other detecting BGP hijacking attacks. And so in both of these projects, what we needed to do was, at a fine time granularity, rebuild sort of this, or have a global state of BGP so that we can look for interesting events. So in the case of outages, what we're looking for are large numbers of prefixes that have been withdrawn simultaneously that could be indicative of an outage. So for example, in the case of some extreme weather event, a part of the country is affected, we would end up seeing a bunch of prefixes being withdrawn for that area. Censorship also manifests in this way. And then for our hijacking project, we're monitoring for suspicious prefix announcements that could be indicative of hijacking. So the part that the diagram that I've highlighted here, these are some components that we built on top of BGPStream, on top of BGP Corsaro, that we use to do this kind of sort of real-time analysis and monitoring of BGP data. And so over the next couple of slides, I want to highlight that, so not only can you use BGPStream to do this kind of stuff, but there's actually several challenges that we ran into that we chose not to solve in the core part of BGPStream, and instead have deliberately deferred to the application because it ends up being that different applications have different requirements here. So the first challenge that we came across, so in both of these projects that we have, one of the prerequisites that we had was to have a global view of BGP at a fine time granularity. And so what this means is we wanted to have sort of this per peer view of a peer's routing table at 1 minute granularity. Now, of course, the route views write-first projects don't make table dumps available at 1 minute granularity. And so in order to get this information, we have to rebuild or infer the peer's state based on the updates that we get. And so to do this, we took BGP Corsaro, we created a plugin for it that we called routing tables. And then we use a finite state machine, and then, pretty easy to understand, we take the rib dump, we take the table dump as this sort of sync frame, and then we apply the updates as incremental patches to that. And so there's some more details about this in the paper, but we actually did some validation against the explicit table dumps that we get from this data, and we found that indeed in this process we have these really, really low error rates. Okay, so then, we're processing a ton of data that's coming from a lot of different vantage points. And so the next thing that we wanted, the challenge we ran into in this case was just data reduction. We wanted to reduce the volume and computational complexity of the data we're processing. And so the intuition here, and it's really pretty straightforward, is that there's a lot of redundancy in these BGP messages that we're getting. And so even at this 1 minute granularity, we're getting these inferred peer snapshots every minute. And so we just simply diff 2 successive snapshots, and then we only publish the things that have changed. And so actually in this case, we still find that even at this 1 minute granularity, we see this 3 times reduction in the volume of data when we compare this to the raw update stream. Okay, and then finally, the last challenge that we have really comes from this fact that we're processing data that's coming from a set of collectors that are globally distributed. And so these collectors are making their data available on these archive websites with variable latency. And then, of course, sometimes things go wrong and they don't make their data available at all. And so as an application here, because we want this global view of the routing system, we need to buffer these per-peer tables while we wait for data from other collectors to arrive. And so just as in a typical synchronization problem, we have this trade-off between the amount of data that we're willing to buffer, the latency, so how long we're willing to wait for data to be available, and then the completeness, so how much data do we need to have in order to be able to do our analysis correctly. And so some applications, you can imagine might need data as soon as possible, no matter how complete it is, while others really need data from as many peers as possible in order to do their analysis. So we have these, as I was been saying, we have these two applications. In the case of hijacks, actually, we want to tune the system for lower latency because we're going to send active measurements in response to announcements that we see in order to get more information about the hijacking. So the way that we've done this, and we've done this in a system that we're able to support multiple applications that each have different synchronization requirements with one underlying data architecture. And so to do this, we use this sort of simple, or at least conceptually simple, metadata-based gating mechanism. And we're doing this, using our BGP Corsaro plugin that's outputting our per-peer routing tables. These tables come every minute, as I mentioned. And then when a Corsaro instance publishes a snapshot into Kafka, what happens is it also publishes a little bit of metadata that says, hey, I published this table, it's for this time, it's about this collector. And then we have another synchronization server that's watching those metadata messages. And it's these synchronization servers, we run multiple of these, and each one of them is tuned specifically for an application's needs. And so, in that trade-off that I talked about before, you might have a synchronization server, for our hijacks example, which is tuned to have low latency. So it's tuned so that once you see the first snapshot from a peer, you can only wait this amount of time before it's time to publish whatever you have available. So then it watches the metadata as it arrives, and then once that criteria has been satisfied, publishes another little bit of metadata into Kafka, at which point our application consumers have been blocked waiting for that message, and then once they receive it, they then go ahead and retrieve the actual data from Kafka directly. And so in this case, we're able to, with this really low overhead per application, support multiple really quite different applications, have different end uses, or sorry, different latency and completeness requirements within this one application where we don't have to replicate the data, we don't have to replicate the processing of the data. Okay, so this is about going to do it for me. I have a couple more slides. First of all, we are definitely not alone in this space to modernize and improve the state of the art in BGP measurement, BGP analysis and processing. As I've mentioned, there's the OpenBMP project at Cisco. I'll talk about that a little more on the next slide. Both RouteViews and RightBris are working to improve their data collection infrastructure to provide lower latency access to data. And then there's some guys at Colorado State with BGPMon who have developed this Cassandra-backed way to query BGP data. And indeed, there has been some coordination between these efforts. We hosted a hackathon last year at CADA in collaboration with RouteViews, Right, and BGPMon. And then, we have this ongoing collaboration with the BMP developers. And so in all of this, we really see BGPSTREAM as being complementary to this work that's going on to advance the state of the art here. What we're trying to do is allow users to gain easy access to any of this public BGP measurement data and as these things come online, we want to be able to do this in a way that requires them to make few or no changes to their analysis code. So what's coming up for BGPSTREAM? We have a version 2 release coming out later this year. Most importantly here, this is going to ship with native BMP and OpenBMP support. And we're currently working actively with the OpenBMP guys to add this support to BGPSTREAM. We're going to include some better filtering interfaces. So this is going to be sort of slightly reminiscent of the BPF syntax here. What's cool about this code actually was this was contributed last year at the hackathon. So we've done almost no work to make this code publicly available. And then we also are going to, of course, ship with performance improvements, bug fixes. So outside of code, we are working also on deploying a publicly available OpenBMP collector. And so if you run a BGP router and are willing to contribute public BMP feed to this project, I would love to talk to you. As well, as I mentioned at the beginning, we run this metadata broker web service. It's currently a single point of failure in this infrastructure. We would like to replicate this elsewhere. So if you are capable of hosting this, if you would be interested in hosting it, also like to talk to you. We're trying to do things like load balancing and redundancy here. And then eventually wanting to add support for the RIPERS streaming service. So all of that said, a big part of what I want to get out of this week is feedback from you guys. So if there are things here that you think should be shifted around, if you think there are features that there should be there that aren't, I would really like to hear from you. We have some flexibility to kind of move things around and play with the timeline here a bit. So that's going to do it for me. As I mentioned, it's available there. There's a bunch of really good documentation on the website. We also have a pretty good community on GitHub submitting issues, pull requests, and the like. So I would encourage you to go give it a try. Other than that, I will take some questions.
Robert Kishtaki, RIPE-NCC. I am pretty sure we will volunteer for hosting one of the web apps for you.
That would be great, thanks.
And it's also probably going to be close to at least our data set,
right.
so
yeah.
it could make sense. But I have a question as well. So especially for the so-called big data analysis,
yeah.
so when you want to crunch through, say, 15 years of data,
right.
and in combination that with the fact that you mentioned you don't store the data, you just fetch it from the sources originally. Yeah. So if 10 researchers here jump on it, then we will serve our data 10 times as many times they are restarting their processes, or do you do local caching or something usual?
So the short answer is no, we don't do local caching. The more
Can I add the feature request?
Yes. So the more nuanced answer there is because we're pulling the data over HTTP, we have a couple of ways to go about doing this. One way that we are actually using at CADA is to have a persistent local cache of data. And because we have this metadata broker process in here, we can actually redirect, and we do redirect local users to a cache. So indeed, when we're doing this analysis, we're using a local mirror of that data. And then the other way, which is a little more lightweight, and what we're trying to do we're planning on adding at some point, is let's say, containerized HTTP cache infrastructure that you can spin up, and it would just transparently work with BGPSTREAM.
I don't know if it would be an option, but if users run their BGPSTREAM locally,
yeah.
they contact your metadata server and they figure out what they need,
yeah.
the cache could be local to the user.
That's what we're talking about, yeah. So like a local HTTP cache that you could add. So
and I don't know if that needs to be a feature, but if it is, then I'm asking for it.
Great.
Any other questions? Let me ask one. Sure. Do you think that this could be suitable for people who wanted to use it operationally? They're optimizing routing. They have a lot of peering points. They want to gather their data. Does it perform well enough for something that needs to be production and hardened versus a research usage?
Yes.
Yes. Of course.
I don't know what metrics you're using for perform well enough. You mean efficiency or stability, or what's the
all of the
things?
above, right? Yeah.
Okay.
Yep.
So in terms of stability and efficiency, the library, the framework itself is not going to be a problem there. I think if you are looking at using this publicly available data, there is some collection latency between when it happens in the real world and when it's available for analysis. This is through this current MRT website-backed system. With BMP, or if you have your own local data, then that problem goes away.
Thank you. Okay, if that's all the questions, then I want to call you guys to bring the blue sheets up, and I want to thank Yossi and Alistair again for giving us these wonderful ANRP talks. So that's all blue sheets, and see you next time. And then the other RG meetings the rest of the week, of course.
Sorry? Even
No.
I don't know.